A massive piece of heavy rolling stock represents hundreds of tons of kinetic energy and complex mechanical systems. When it comes off the rails and grinds to a halt for maintenance, the entire operation is on the clock. Traditionally, railway maintenance relies on the periodic overhaul, or POH. This system operates on a rigid calendar. Coaches are pulled from service and serviced strictly based on elapsed time or mileage limits, regardless of how the underlying hardware is actually performing. This diagram illustrates the first major inefficiency of time-based scheduling. As the timeline moves steadily from one scheduled interval to the next, perfectly healthy mechanical components are routinely stripped out and replaced simply because their scheduled time is up. That is a massive waste of usable hardware. But a strict calendar creates a much more dangerous blind spot. Hardware doesn't check the schedule before it breaks. Critical component failures often occur right in the middle of these intervals, leading to sudden breakdowns in the field. Solving this requires shifting the entire model. Instead of reacting to a calendar, modern overhaul workshops are transitioning to condition-based predictive maintenance, driven by artificial intelligence. Relying purely on a schedule leaves you guessing about the actual wear and tear. To guarantee reliability, you need to know the exact physical state of the machine at any given second. Applying AI to a heavy industrial workshop isn't a matter of flipping a single switch. It requires categorizing the technology into specific operational domains. We can map this transformation across a stark 2x2 matrix. These 4 pillars, predictive maintenance, quality improvement, productivity, and safety, form the structural framework of the modernized workshop over the next 5 years. Across all 4 domains, the AI does not operate autonomously. It functions as a high-leverage decision support system, synthesizing gigabytes of raw workshop data but a human could never process in real time. The utility here is clear. The technology doesn't replace the engineer, it acts as a multiplier, allowing human expertise to scale across safety, quality, and maintenance simultaneously. Step inside a modern overhaul bay, and the first task is translating a physical train coach into a digital format. AI drives predictive maintenance by constantly running historical failure data and past maintenance logs against live, real-time telemetry from IoT sensors on the train. Look at this wireframe schematic of a single coach. The sensors specifically target high-risk subsystems: wheel bearings, brake cylinders, air springs, and the HVAC units. All data streams aggregate into a central coach health score dashboard, giving engineers a live pulse on the hardware. Failure prediction happens through pattern recognition. Algorithms scan data for abnormal deviations in vibration frequencies and bearing temperatures. This flags an impending failure early. If temperatures spike, the system alerts the team well before the scheduled calendar deadline. By monitoring the continuous physical state of the hardware, workshops can catch problems exactly when they start to develop. This cuts out unnecessary overhaul costs and sharply reduces the rate of coaches failing in active service. While internal sensors track the moving parts, the exterior presents its own challenge. Manually inspecting the structural integrity of massive steel underframes is a slow, error-prone bottleneck. To solve this, workshops are deploying machine vision. Automated optical systems provide high-volume, high-precision visual inspections without fatigue. These AI-powered cameras are trained on vast datasets of physical defects. They scan continuously for flaws in weld quality, microscopic paint defects, wheel flats, and hidden structural corrosion. This enables smart quality control. In this visualization, the live camera feed of the completed underframe on the left is algorithmically compared against digitized technical blueprints on the right. The system spots discrepancies human eyes miss, instantly highlighting missing bolts or improperly routed pipes. It also reads quantitative markers visually, verifying that torque values are correct and checking for strictly prohibited cable connection errors. By mathematically locking the physical reality of the build to the specification standard, the workshop achieves a high rate of first-time quality and eliminates the friction of downstream rework. The digital overhaul extends to the technicians themselves, targeting the historical friction created by paper manuals and manual inventory tracking. Workshops are deploying digital work instructions to solve this. Technicians equipped with smart glasses receive step-by-step guidance, overlaying 3D models and exact torque specifications directly onto their field of view. On the logistics side, AI manages the parts themselves. By analyzing fleet utilization data and seasonal demand patterns, the system accurately predicts exactly which spare parts the inventory room will need weeks in advance. This predictive data arms workshop supervisors with powerful decision support. They can optimize their manpower allocation, clear bottlenecks, and generate highly accurate coach completion estimates. The final pillar integrates directly with the physical environment: safety. Workshop camera networks continuously analyze the floor to instantly flag unauthorized zone entry or unsafe worker behavior. The parameters are highly specific. The system monitors for compliance with personal protective equipment, detects the earliest signs of smoke or fire, and automatically logs near-miss incidents for review. This continuous data loop feeds directly into worker training. AI tools can instantly convert dense technical circulars and CAMTech manuals into interactive flashcards and standard operating procedures to keep the workforce upskilled. Integrating real-time logistical optimization with continuous safety monitoring produces a workshop that moves highly efficiently while protecting the technicians on the floor. This ecosystem unifies into an automated workflow. IoT telemetry, machine vision scans, and technician inputs funnel down to generate standardized documentation, like error-free POH certificates. But implementation has strict constraints. It requires pristine data, reliable sensor networks, and rigorous cybersecurity to protect the infrastructure. And there is a hard limit to what the software can do. Artificial intelligence is, at its core, a highly advanced pattern recognition engine. It is not a substitute for human judgment when facing complex, edge case engineering problems. These systems are built to automate the repetitive tasks, surface vital insights, and remove the guesswork from heavy maintenance. But when it comes to the safety-critical decisions that keep a multi-ton machine on the rails, the experienced railway engineer retains absolute, final authority.